Hello class, this is CSE 4600, section 62, week 8, fall 2024. Okay, so we're gonna conclude our discussion on deadlock, and keep in mind, in the syllabus it was supposed to be that we would go straight to chapter 3, that's all about memory, but I felt like the discussion on deadlock was a bit easier to understand, so that's why I jumped over to chapter 6 instead. Chapter 6 is all about deadlock. We looked into that last video. And this video is coming out a bit late, and that's because I had to prepare material for other classes' midterms, mainly CSE 4610. So when it comes to your midterm, the plan is this. I'll have it be available during week 9, and you're going to have about 2 days to complete your midterm. You're also going to get a study guide that outlines the topics that will be covered in the midterm. I will likely have that available sometime this weekend. But for week 9, it's just going to be your midterm, so there's going to be no other material left for that week. Though I might give out a supplementary video outlining the topics to be covered in your midterm. So anyway, your midterm is going to cover everything that we've talked about so far. What is an operating system? What is a process? What is a thread? What is synchronization? What synchronization methods are there? What is a race condition? And finally, what is deadlock and what can we do about it? So we're going to conclude our discussion on deadlock and deadlock prevention. To recap, there are 4 conditions for deadlock and 4 ways we can deal with deadlock. The 4 conditions are mutual exclusion, hold and wait, no preemption, and circular wait. And if we have those 4 conditions, we have deadlock. There are also 4 ways to deal with deadlock. The first one is not dealing with it at all. The second one is let it happen and detect when it happened, and if it's happened, do something to recover from it. So that's deadlock detection. The third one is deadlock avoidance. That's what we're going to look at today. And the fourth one is deadlock prevention, keeping deadlock from happening in the first place. So, to recap, do nothing about deadlock, let it happen, and detect when it happens. Deadlock can happen, but we're going to steer clear of any scenario in which deadlock can happen, and keeping deadlock from happening in the first place. So this is just a recap from the last video where we talked about deadlock detection with multiples of each resource type. So we need 4 data structures here. The first are 2 vectors. One is a vector of every resource in existence in our system. That's vector E. Vector A is the number of each resource that is available, not yet been allocated to anything. The third one, the second one was A. The third one is C. This is the amount of resources allocated to each process. Each row is how much of each resource has been allocated to a process. That's C. R is how much of each resource each process still needs. So each row is a listing of how much of each resource that process still needs. And then there's a property where if we add up the columns of C and add them to the corresponding values of A, we get E. So that's a property to know. Deadlock detection is based on determining whether some requests can be fulfilled. We say that a request vector R is less than A if, for each corresponding value, that value in R is less than that value in A. And this is the algorithm for deadlock detection. We're going to look for an unmarked process PI for which the ith row of R is less than or equal to A. If such a process is found, add the ith row of C to A, mark that process, and go back to step 1. We're going to repeat step 1 and 2 repeatedly until we mark every process or we find out that there is... If no such process exists, then the algorithm terminates. If the algorithm terminates and there are unmarked processes, then those processes are deadlocked. So let's try this out with an example. So here in this example, we have 4 tape drives, 2 plotters, 3 scanners, and 1 Blu-ray drive in existence. Of those, 2 tape drives and 1 plotter has not yet been allocated to any processes. The rest have been allocated to processes, and those processes still need more resources. So process process 1 currently has a scanner, but it needs tape drives and a Blu-ray. Process 2 currently has 8 tape drives and a Blu-ray, but it needs a scanner. Process C has a plotter and some scanners, but it still needs another plotter and the tape drives. So here's how we're going to run our deadlock detection algorithm. We find a process's request vector that is less than or equal to the available resource vector. So let's look at process P1. Let's look at process 1 here. Is this request matrix, is this row in the request matrix less than the available resource vector here? 2, 2, 1, 0, 0, 0. Oh, here's a problem. Process 1 needs a Blu-ray drive, but we don't have one available. So no, we cannot fulfill process 1's request. Can we do that with the process 2 request? 2, 1, that's good. 1, 0, that's also good. Oh, no problem. Look. Process 2 needs a scanner, but we don't have a scanner left. So no, we cannot fulfill process 2's request. But can we do anything with process 3's request? Check this out. 2, 1, no, 2, 2, 1, 1, 0, 0, 0, 0. Yes, 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 we have resources that we can give to process 3. So, now, once we determine that there is a resource request that can be fulfilled, here's what happens next. We cross out that row in the request matrix, and then we add this entire row back to vector A. We're going to increment all the values in A using this vector here. What would really happen is this. These resources get allocated to process 3. These would go down to 0 because they're all in use. And after some time, process 3 is going to use those resources, and then it's going to terminate. That means it's done processing. And then it's going to release all those resources back to the pool of available resources. So now we have more resources available. We're just preempting those steps by crossing out this row in the request matrix by zeroing out all the values, and then taking all these values, adding them back to here, and then zeroing out this row. So after that, we now have 2 tape drives, 2 plotters, and 2 scanners available. Can we fulfill another request given these resources now that we know that process 3 can terminate? Yes, yes, you can. Because look, in the case of process 1, it still needs a Blu-ray drive, but we still don't have that available yet. But we do have enough resources to fill process 2's request. So we gotta zero out this row and then add this row back to this vector here. After that, we zero out the request and allocations for process 2, and now we know that process 2 has terminated. But look at our pool now. We have even more resources available. And the Blu-ray drive that process 1 needed. Process 1 needed 2 tape drives and 1 Blu-ray drive. And we have that already. So what would happen next is this row here would be zeroed out. and then this row here would be added to this row. And at that point, every process has been marked, and that means every process can run to completion. There are no unmarked processes left. We don't have deadlock. So, consider a different scenario in which process C also needed a Blu-ray drive. We know from the previous example that process A's request could not be completed because we didn't have a Blu-ray drive. Process B's request could not be completed because we didn't have a scanner. But now, if it's the case that process C also needs a Blu-ray drive, we can't complete that either because we're out of Blu-ray drives. They're all allocated to other processes. In this case, if this was the current state of the system, and we ran this algorithm, then we discovered that we have deadlock. Now what? Well, now we need some way to recover from deadlock. Once we detect deadlock, we need some way to recover from it. And there are a few options to that, and they all have their own downsides. The first thing we can try to do is to try to preempt resources. We can take away resources from processes and then giving them to other processes that need those resources. In some cases, we might have to do that manually, and for some resources, this is downright impossible. So in that case, we may need an alternative approach. Your system might be saving a checkpoint every now and then. So if the current state of the system is deadlocked, all we gotta do is reload one of its checkpoints from a checkpoint file and then restore the state of the system at that point in time. From there, we can simply reallocate resources differently and see whether we eliminate deadlock that way. Another way, okay, the only problem with a checkpoint is now you need a checkpoint file. Or you might need several checkpoint files, because what if it's the case that you rolled back, but what if it's the case that when you rolled back, that previous state was also deadlocked? Now you're trying to save scum your entire system. Well, you really shouldn't say save scum. I guess the more proper term is backup. Make backups, everyone. So the only problem with a checkpoint is that you may need to save several checkpoints, because it might be the case that one of your checkpoints was also deadlocked. So you have to go to an even earlier checkpoint and reload the system state from there and see if you can do anything different that doesn't lead to deadlock at that point. If all else fails, start killing processes. Okay, so some processes are going to be in a deadlock. You might think that you can start eliminating deadlock by killing off those processes in the deadlock and freeing up those resources. That's not always the best target. Oddly enough, a better target would be to kill a process for which restarting has no ill effect. To kill processes like this, it's also not the best solution, because if the resources in question are, for example, values in a database, then what happens is this. This process will have done some work on the database. It may have written some files. It may have written some values to the database. If we restart that, any work that the process has done prior to deadlock, it's going to do it again, and we're going to have the wrong values in the database. So that's not good. So, yeah, there is a problem with all of these. And my point is this. Sometimes we might not be able to recover from deadlock in this way. But, so recovery from deadlock has issues of its own. Can we avoid deadlock altogether? Can we allocate resources in such a way that we can avoid the possibility of deadlock? Well, here's how we do that. In our discussion in deadlock detection, we actually made an assumption, and it is this. When process requests resources, they know exactly how many of each resources they're gonna ask for, and they're gonna ask for them all at once. That usually is not the case. What happens is processes request for resources one at a time. If, for example, you're doing a floor remodel and you want to tile your bathroom floor, what you would not want to do is get the exact amount of tiles you need. Really what would happen is you would get a little bit more than that, because there's a possibility that you might break a tile, or a tile might break in the future and you need a spare. Measure twice, cut once, but what if you screw up and you miscut a tile? Or as you cut, the tile broke in the wrong way and you need a spare tile. That's what I mean by you might not know how many of each resource you'll need ahead of time. I guess another construction example is you are doing some foundational work on a job site and you rent a backhoe, but the soil is much harder than you expected and you need some other equipment to break up the dirt. So you need to bring in, say, another backhoe to help out with digging up the ground to start building the foundation. So these real-life examples are basically saying you might not know ahead of time how much of each resource you'll need. Also, I guess another example is this. If you are painting the walls in a room in your house, for example, and you determined that you need 2.7 gallons of paint, are you gonna get 2.7 gallons of paint? No, they're gonna have to round it up because they sell paint by the gallon. What if you miscalculated and you actually needed like 3.4 gallons of paint? Now you have to go back to the store and get another gallon of paint. My point is this. We might not know how many of each resource we're going to need ahead of time. And with finite resources available with finite resources on the operating system, when processes request resources, we gotta determine whether doing so leads to a safe state. So let's talk about a safe state. So we can visualize it using a resource trajectory. So this is a graph where the x and y axes represent progress being made by each process. So process A is horizontal. So process A is the horizontal axis. Movement across this axis, any movement going to the right is progress being made by process A. The vertical axis is process B. Any vertical movement is progress being made by process B. There are going to be some regions in which these processes will need some resource. So process A is going to need a printer at instructions 1 to 3, and it's going to need a plotter at instructions 2 to 4. Process B is going to need a plotter at instructions 5 to 7, and a printer at instructions 6 to 8. Horizontal movement on this trajectory corresponds to progress being made with process A. Vertical movement corresponds to progress being made for process B. Wherever we switch from horizontal movement to vertical movement is where the CPU made a context switch from one process to another. And there are no diagonal paths because only one process can advance at a time. So now that we know where each process is going to use a resource. So what happens if we overlap those regions? Let's look at the printer first. So process A needs a printer at instructions 1 to 3, and process B also needs a printer at instructions 6 to 8. we can overlap those two regions and get this purple area here. And this is where it's interesting. That region represents where both processes are using the printer at the same time, which is impossible if there's only one of each resource type. So it means we cannot enter this region at all. And the same is true for with the plotter. So the plotter is used by process A at instructions 2 to 4. The plotter is used at instructions 5 to 7 for process B. There is an overlap region here where both processes are using the plotter at the same time, which is impossible. And if we take the overlap of those two overlaps, that is the region in which both processes are using both resources at the same time, which is just as impossible as using just one resource at the same time by both processes. So now we have a roadblock. This is basically an obstacle for our resource, the trajectory path. So we cannot enter these regions at all. You see where this is going? This is the intuition here. You are drawing a zigzag path across this space where your only legal moves are going right or up. You must traverse this space such that you don't get trapped in a corner like this, because again, we can only move right or up. If we try to move up here and try to move right, we cannot traverse this path because of the obstacle. That means if we enter this red region here, no matter what we do, we're going to get deadlock. Once we enter this red region here, that anything we do in that region will only lead to deadlock. And deadlock is the only outcome for this region here. Once you hit this corner, specifically, that's where you get deadlock. So the idea is this. You are drawing some zigzag path across this space such that you go from the start to the end while avoiding any areas that would lead to deadlock. You don't get trapped in corners like this. If you are on the boundary of this red area, if you're on the boundary, then your only move left, in this example, we cannot move up because that we would be entering the area in which we would end up getting deadlock. Our only move left is to move right. Basically, we are suspending the operation of one process so that the other process will do all its work needed with these two resources. And once we've skirted around this impassable area here, we avoid this unsafe area in which no matter what we do, we end up with deadlock. Once we enter this red area, we're stuck and the only outcome left is deadlock. But if we're on the boundary, there's still a way out, and that's just to traverse the boundary instead. So that's the intuition behind a safe state. It's basically anywhere in this space where we can still move right and up and still be able to reach the finish point here. Because once we enter this red region, we cannot move anywhere. We cannot move this way because then we hit an obstacle here. We cannot move. We can move this way, but only on the boundary. Once we're inside this red area, we hit this boundary and we can't go anywhere, and the only move left is deadlock. So this is the intuition behind a safe state. It is anywhere in this space such that we don't end up getting deadlock. We don't run into obstacles like these impossible areas where both processes are using the same resource at the same time. Unless there's a second printer, then we kind of solved it in a different way. Anyway, we're going to look at our deadlock avoidance algorithm. It's going to be based on the information from the previous diagram. At any time, there is a current state consisting of four things: the existing resources, the available resources, the currently allocated resources, and the requested resources. A state is safe if there is some scheduling order in which every process can run to completion, even if all of them suddenly request their maximum number of resources immediately. So let's look at this example. Is this a safe state or is it not a safe state? What do I mean by safe state? Basically, is there a sequence of steps that we can take in which every process will terminate, even if they request for the maximum number of resources? Well, let's look at this first. We know that processes A, B, and C have 3, 2, and 2 resources allocated respectively. And if we combine that with the 3 free available resources, we know there are 10 resources in existence. We also know that each process may need a maximum of 9, 4, and 7 resources. So, what we're looking at is not whether each process is going to terminate, but here's the thing, we're not doing calculations based on whether each process is going to terminate. We're looking into the future to see whether they can terminate. Each process might not need the maximum amount of resources listed here. It might, but it's possible that it might not. So what we're doing is looking into the future to see whether, starting at this state, every process can terminate without deadlock. So let's try it out. If we subtract max from has, we know that process A will need may need 6 more resources. Process B may need 2 more resources. And process C may need 5 more resources. We know we have 3 free resources left. If it is the case that process B is going to need its maximum number of resources, if process B requested its maximum number of resources, is there enough that we can give it those resources? Yes, because we can't fulfill process A or C's maximum requests. So what we can do is, at this point, we're simulating what would happen in the future. And it's this. We give 2 resources to process B, and it's going to terminate and release all of its resources eventually. We can take those 5 resources and give them all to process C. It's going to terminate and release those resources eventually. And now we're going to have enough to fulfill process A's request. Which means there is a sequence of steps in which every process terminates without deadlock. We found a sequence of steps in which, starting at state A here, we can fulfill each process's maximum request and still be able to have every process terminate without deadlock. What if instead there was one change in that initial state? I guess put it another way. What if process A requested, I need 1 more resource. Process A says, I need 1 more resource. What we do is we imagine what would happen if we allocated one more resource to process A. And then we play the same game to see whether those processes will terminate then. If every process terminates, then we can say that this is a safe state, then therefore we can fulfill process A's request. If it does not lead to a safe state, if it leads to deadlock, then we cannot fulfill process A's request. So let's say, what if process A says, let's say process A requests 1 more resource. Let's see what happens. Well, now we have process A with 4 resources, and it might need a maximum of 9 still. Process B can run until it requests 2 more resources. At which case, we're gonna give to process B 2 more resources, and then it's gonna use them and free them up. After that, now we're stuck. Process A needs 5 more resources, which we don't have. Process C needs 5 more resources, which we don't have. So what this tells us is, if process A says, I need 1 more resources, deny that request, because it's going to lead to deadlock if we do that. We know this state was safe because we had found a sequence of steps in which every process was going to terminate. But if process A says, I need 1 more resource, and you determine that it does not lead... If process A says, I need 1 more resource, and you determine that it's going to lead to deadlock, you deny that request. It's important to note that this unsafe state is not a deadlock state. It can lead to deadlock, but it's not guaranteed that it's going to lead back to a safe state. It's possible that a process may finish without requesting any additional resources, or it might release some of its resources. Each process may need more resources than what it has allocated, but maybe not. With an unsafe state, it's not guaranteed that every process will finish. With a safe state, we know it's guaranteed that every process will finish. So Edgar Dijkstra came up with yet another algorithm. You're gonna hear Dijkstra a lot in computer science, if it wasn't clear enough. We have Dijkstra's pathfinding algorithm, for example. We have the Dining Philosopher's thought experiment from earlier. Now we have the banker's algorithm. The banker's algorithm is based on how a bank would loan out money only if the banker knew that that money would be repaid. This algorithm checks whether fulfilling a request for resources leads to an unsafe state. If it leads to an unsafe state, that request is denied. If not, the request is fulfilled. In this analogy, you can think of processes as customers and resources as credit. Consider 4 processes that need up to 6, 5, 4, and 7 resources. Not every process is going to request that maximum right away. So it's going to ask for some amount smaller than that. Which is good because there's only 10 resources to go around. That algorithm fulfills requests for processes such that there is a sequence of steps that does not lead to an unsafe state. So let me get out of this for a little bit, and I do have an ink replay that you can see. So this is how we know that this state here, B, is safe. So we start here where every process has not requested for anything yet. Sometime later, we're going to be at this state. What we're doing is looking into the future to see whether, starting from that current state, we have every process terminating. So here's how we do it. It's going a little bit fast, but yeah. Maybe I have to slow it down. But anyway, my point is this. Okay, so we start with our 2 resources, and process C might need 2 more resources. If we assume every process is going to ask for its maximum resources, we're going to determine whether it's safe to do that. So process C is going to request for 4 resources, for its maximum of 4 resources. But we have 2 resources to give to process C, which already had 2 resources. That request can be fulfilled, we cross it out. And then we're going to have enough resources left over to fulfill process B's maximum request. We hand those resources over, and now we have 5 resources at our disposal. We give those resources to process A, and now after that we have 6 resources at our disposal. Process D, and now we have enough resources at our disposal to fulfill process D's maximum request. And now we know that this state is safe. We're basically looking into the future to see whether each process will terminate. If we get some request, we see what would happen if we fulfill that request. If that request leads to deadlock, we reject the request. So here's an interesting one. What happens if we have this state here? So if you do some math, we subtract max from has, we determine that process A needs 5 more resources, process B needs 3 more resources, process C needs 2 more resources, and process D needs 3 more resources. But we only have 1 resource currently available. That's going to lead to deadlock. So now we know that this is an unsafe state. There is no way there is no sequence of steps in which every process terminates. So let's play that one. No. Give me a minute. Okay. So this is an unsafe state because there is no sequence of steps in which we can have every process terminate. So state C here isn't safe, but state B here, as we saw in a previous slide, that was safe. We can also apply this for multiple resource types. So the left matrix is how many resources are assigned to each process. The right matrix is how much of each resource each process may still need. So this one's a little bit complicated, but I'll just play it in a little bit. Basically, to determine whether we're in a safe state, we check whether every process can finish their work if every process requested their maximum resources, given the amount of resources unallocated. So we have 1, 0, 2, and 0 resources available. Each process is going to request we're going to assume that every process is going to request its maximum. Like, I need this right now. So let's play it out. Let's cross that out. That one can be fulfilled, so we can cross these out. Now this is our available pool. We can fulfill this request. 5, 1, 3, 2. Now we can fulfill that and cross that out. 5, 2, 3, 2. Cross that out, and there we go. 6, 3, 4, 2. Cross that out, and it's safe. Yeah, it takes a little bit of work to do that, by the way. So here is the algorithm for that. Given a request, create a new state and perform the following algorithm on the right. Look for a row R whose unmet resource needs are smaller than or equal to A. If no such row exists, then the system will deadlock. The system will eventually deadlock. Assume the process of the chosen row requests all the resources it needs, which is guaranteed to be possible, and finishes. Mark that process as terminated and add all of its resources to the vector A. Repeat steps 1 and 2 until either all processes are marked terminated, in which the initial state was safe, or no process is left whose resource needs can be met, in which case the system was not safe. If, when this algorithm terminates, every process is marked, then we know that that was a safe state. If not, so basically we apply this algorithm to some request and see what happens. If we end up in an unsafe state, then we reject that request. If we end up in a safe state and it's possible for every process to terminate, we accept that request. So that's how it works. So really there should be a step 0 to this. And that step 0 is, given a request, create a new state and perform these 3 steps on that new state. If, when the algorithm terminates, every process is marked, then fulfilling that request results in a safe state. Fulfill that request, that new state becomes your current state. If there are unmarked processes, then fulfilling that request results in an unsafe state. Reject that request, no state changes are saved. Also, it's possible that there might be more than one eligible process at step 1. Just pick one, doesn't matter. So, yeah, Now we have an algorithm in which we can avoid deadlock altogether. But there's still a problem. And it is this. As great as the banker's algorithm is, it's hard to implement in practice because processes don't know how much of each resource they need in advance. And it gets worse than that. The number of processes on a system is in flux. Processes are created and terminated over time. So we can't use the banker's algorithm. The next best thing is to use some heuristic that works like the banker's algorithm most of the time. If you've ever heard of what an algorithm is and what a heuristic is, or I should say, if you don't know what an algorithm is, it's some sequence of steps that you take, and it will 100% give you a solution every time. If it falls any short of that, that's not an algorithm. That's a heuristic. Heuristics don't always provide the correct solution. If an algorithm gives you the correct solution 100% of the time, then it is an algorithm. Any less than that, even if it's if it's any less than that, even 1/4 of a percent less than that, that's not an algorithm. It's a heuristic. Okay, so deadlock avoidance has the problem of we need to look into the future to know how much of each resource each process is going to ask for. We need a crystal ball for that, which only exists in thought experiments and simulations. Deadlock avoidance has the issue of knowing future requests. Some things in computer science have this problem, where we need a crystal ball. We need to look into the future to know what to do. We don't have crystal balls in computer science. Not outside of thought experiments and not outside of thought experiments and not outside of simulations. We don't have crystal balls in computer science. Remember how there were 4 conditions that had to be met for deadlock to exist? If we can negate one of those, we can prevent deadlock from happening at all in the first place. So which one do we negate? We can try out each one by one and see what happens. Can we negate mutual exclusion? Basically, if processes can share resources, and that one resource can be shared by more than one process, then we would not have deadlock. Is this doable? No! Imagine if a printer could be used by more than one process. That output would be chaotic. Like, imagine if you're printing out sheet music. Imagine if 2 people were trying to use the same printer at the same time. One user tried to print out sheet music and the other user tried to print out their thesis. Imagine what that would look like. It'd be a mess. There are some other problems with this that's outlined in your textbook, but this gives you an idea of why we would not want to negate the mutual exclusion condition. There's one thing we can do, and that is don't assign resources to processes unless it's absolutely necessary. And make sure that as few processes as possible try to claim that resource. So that's one thing we can take away from trying to attack the mutual exclusion condition. So no, we cannot do anything about mutual exclusion. Can we try the hold and wait condition? If processes requested everything they needed in all in one go, then we would not have deadlock. Is this doable? Also no. And the problem is this. Processes don't know how many of each resources. The problem is processes don't know how much of each resource they need. If they did, then we can use the banker's algorithm, not the banker's heuristic. And here's the other problem. If processes request everything in advance, if processes request everything they needed all in one go, it might be an inefficient use of resources. For example, if a process needs a tape drive and a printer to print results, what if that process took 1 hour to find the information it was needing on that tape drive? Then that printer will have been idle for an hour when it could have been used by other processes. that printer was allocated for an hour, plus however much time it needed to print stuff. And most of that time was spent doing nothing when it could have been printing other stuff for other processes. So no, for that reason, we can't attack the hold and wait condition. Can we try the no preemption? Can we try the no preemption condition? Well, also no. No. Let's go back to the printer. Let's say we're trying to print stuff. And we try to preempt the printer in the middle of a print operation. Now that output is incomplete. There is one thing we can do with the no preemption condition, and that is virtualizing resources. So we make it look like there are more resources available than there are actual physical resources. You'll see virtualization in memory, and that is where we fake the presence of more memory than what we have physical memory. And computers do this for the convenience of programmers, because programmers will then see a large contiguous memory space. It might not eat all that space, and that's fine. Due to paging, we can simply just... A process will only use as much memory as it needs. And if that's an idle process, then we can just have the process be moved to some backing store, and then use that memory for other processes. We'll talk about paging and all that in chapter 3, by the way. We can virtualize resources, but not all resources can be virtualized. Database records can't be virtualized, for example. Okay, so we looked at 3 conditions and none of them can be taken down. There is one more condition that we can take down, and that is the circular wait condition. And yes, there is a solution here. And the simplest way to attack the circular wait condition is to have processes request resources in a specific order. If 2 processes need a tape drive and a printer, you require them to request them in the same order: tape drive and then printer. If one process requests a tape drive and then a printer, but then another process requests a printer and then a tape drive, the tape drive might be taken by one process and the printer might be taken by another process. And when those 2 request the other resource that they still need, we get deadlock. If we require both processes to request resources in the same order, let's see what happens. One process requests the printer and it's allocated to that process. The other process tries to request the printer, but it's already in use. So that other process is gonna have to wait. And because that request hasn't been fulfilled yet, it can't request for the next resource because it doesn't have the first resource yet. So here's a proof of this. Suppose we have processes P1, P2, and P3, and resources R1, R2, and R3. We assume these processes are in a circular wait and are therefore deadlocked. P1 is requesting R1, R1 is allocated to P2, P2 is requesting R2, R2 is allocated to P3, P3 is requesting R3, R3 is allocated by P1. The requirement is this: we are to request resources by ascending numeric ID. That is basically another way of wording. Okay, so when we say that processes request resources in a specific order, one way we can enforce that is by giving resources a unique identifier, a unique ID, and we say you can only request resources by increasing ID. That's just another way of implementing this request resources in a specific order thing. We have a function that, given a resource, it returns the ID. In this setup, it should be the case that when P1, it should mean that the ID for resource 1 should be less than the ID of resource 2. And then the ID for resource 2 should be less than the ID for resource 3. And then that means the ID for resource 3 should be less than the ID for resource 1. By the transitive property, this also means that the ID of resource 1 should be less than itself, which is impossible. We have a proof of contradiction. We had assumed there was a circular weight, and then we found a contradicting statement, meaning we've proven that there cannot be a circular weight. We represent a proof of contradiction using a downward zigzag arrow, or at least that's how I do it, simply because I think it's fun to draw. There are other symbols that also mean proof by contradiction. It's just, as I said, I like the downward zigzag arrow. And if we don't have circular weight, then we can't have deadlock. Also, this proof works for any number of resources and then any number of processes. So it means now it's up to us as a programmer to implement some enumeration protocol, which can be difficult to do if there are like thousands of resources. But if we have some basic code that says 3 processes need to use like 3 resources, then if we know it's going to be restricted to those 3 resources, then all we got to do is enforce some order in which processes request resources. And that is how we attack the circular weight condition, and that is how we can eliminate deadlock. Here's a summary of all the approaches we looked at. Mutual exclusion, hold and wait, no preemption, and circular weight. Of these 4 conditions, the best one to tackle is circular weight. And we do that by having processes request resources in a specific order. And we can enforce that by simply enumerating resources and enforcing a rule that, for example, says request resources in ascending order. There are a few other issues related to the topic of deadlock, and we're going to look at them here. The first one is two-phase locking. A common operation for databases is for a process to lock it's going to request locks for several records and then update them all at once. This is called two-phase locking, and there's a danger for deadlock if there's multiple processes involved. In the first phase, the process tries to lock all the records it needs one at a time. No changes are done. Once that process has locked all the records it needs, it does all the changes it needs to do on those records, and then it unlocks all of those records. If a process fails at performing the first phase, such as when another process has locked one of the records it needs, then it releases any acquired locks and starts over. This kind of sounds like the negation of the hold and wait condition, because check this out. We have a process requesting resources all in one go. The problem is this two-phase locking isn't generally applicable here. In real-time systems, it's unacceptable for a process to terminate a job partway and start over. Neither is it acceptable to start over if a process had already made changes to files. So, that start over thing. My point is, this start over thing can't always be done. Because once you've made changes, you can't roll them back. Here's another type of deadlock. The deadlocks we were discussing in this chapter so far are all communications deadlocks. No. They were all resource deadlocks, I mean. The other type of deadlock that can happen is called a communication deadlock. We prevent this type of deadlock by using timeouts. Everything we've discussed so far to preventing deadlock doesn't really work with communication deadlock. So, we prevent communication deadlock by using timeouts. When a message is sent from one process to another, a timer starts. Tick, 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 tick. If the timer goes off before a reply arrives, the process resends that message. Send a message. Tick, 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 tick. Okay, it's 5 seconds. I did not receive a message. I'm gonna resend that message again. Tick, tick. Oh, I got the reply. If you send that message and you don't get a response, then the assumption might be it got lost in transit. But what if it didn't get lost? It was just delayed. Sometimes the message that you were sending wasn't lost, but was instead delayed. In that case, the recipient may end up receiving the same message multiple times. Imagine if the message was, add $1,000 to customer's bank account. You send that message, but you didn't receive a reply back saying, I got the message. So you sent that message again. But that first message wasn't lost, it was delayed. So now you've sent the message, add $1,000 to the customer bank account, twice. Oops. The set of communication rules, that's the protocol. It must be designed to prevent this kind of shenanigans from happening. This is its own complex subject that's unfortunately outside the scope of operating systems. Here's another kind of deadlock that can happen. It's called live lock. Sometimes processes try to be polite to one another by giving up a lock so that another process can use that resource. Sometimes this goes too far, and now you have processes saying, no, you first, no, you first, no, you first, no, you first, and no progress is being made. Processes aren't deadlocked, but they're not making progress either. It's a live lock. And sometimes this happens in real life too. Check out this example where we have 3 cars at a 4-way intersection. Who goes first? And this commenter says it best. When this happens in my town, no one goes. It becomes a standoff of, no you go, no you go, no you go. And no one goes anywhere for a while. This is a live lock. And what this does is it holds up traffic for some time. This is why we have certain traffic rules meant to prevent this kind of live lock. And finally, starvation. In a dynamic system, requests for resources happen all the time, and a policy is used to decide who gets which resource when. The problem is sometimes processes never get the service they need, even though they're not deadlocked. This is called starvation. There are a few ways to prevent this. One way is to use a first come, first serve allocation policy. Or you can increase the priority of whatever process requested a resource. So that way, over time, its priority will become high enough that the system will notice it and give priority to that process so it doesn't face starvation. Note, not everyone makes this distinction between starvation and deadlock because in either case, there is no forward progress. But others do make this distinction. A process can try something n times and try something else if all n attempts fail. A blocked process has no such choice. That is the distinction that not everyone makes, that this textbook does make. So, that's the end of Chapter 6. Your midterm is going to be on Chapters 1, 2, and 6. Expect to see a study guide sometime this weekend. Okay? Alright, that's gonna be it from me for now. Expect that study guide this weekend, and maybe a supplementary video reviewing everything on the midterm. Right, with that, I'll see you later, and we're gonna look forward to our midterm, and after that, we're gonna finally cycle back to Chapter 3. Alright, thank you.